Let's say that we have a parallel RLC circuit. Let me get something going real quick here. So here's R, L, and C. And we know that all three of these guys have a common voltage. I'm going to call it right here, V of T. And we did some math earlier where we applied Kirchhoff's current law at a top node, got an integral differential equation, took the derivative of both sides and all that kind of noise. And what we wound up is an equation that looked like this, where we had is equal to 0. And I am going to point out, I'm going to call this guy right here A, and this guy right here B, and point out that alpha, which is 1 over twice RC, is exactly equal to 1 over 2A, and B, omega naught, which is equal to the square root of 1 over LC, is exactly equal to the square root of B for a series, a parallel RLC circuit, right? So skipping all the math that got us to that differential equation, because that wasn't particularly difficult. Now, let's look at a series RLC circuit. R, L, and C, and there was a common current I of T like so. And we wound up getting a differential equation of the form, the second derivative of our current plus R over L times the first derivative of our current plus 1 over LC times our current was equal to 0. Let's call this coefficient again A, this coefficient again B. And we found for this series RLC circuit that alpha was R over 2L, which again is simply 1 over 2A, and omega naught was 1 over LC square root, which is again the square root of that coefficient B. So what we have observed thus far is that if we can get a second order differential equation where we don't have a coefficient on the squared term or the second derivative term, we can determine alpha just by taking this coefficient and dividing it by a factor of 2. Sorry, that shouldn't be 1 over, it should be A over 2, not 1 over 2A. I'm sorry, my algebra in my head got dumb there. A over 2 and A over 2. I apologize for that. So we can figure out what alpha is by simply dividing this coefficient A by 2, and we can figure out what omega naught is by simply taking the square root of this coefficient B. That is true for any 2 energy storage element circuit, so any general RLC circuit. So now we are no longer constrained by the fact that we need to have a series RLC circuit or a parallel RLC circuit. So let's put this into practice and look at a general RLC circuit. So let's say that I have the following circuit. And for the sake of argument, DS is 24 volts, L is 2 henries, C is 0.2 farads, R1 is 4 ohms, R2 is 8 ohms, and R3 is 12 ohms, okay? So let's start off with something that I believe to be a fairly simple question, but does everybody understand why this isn't a series RLC circuit and why it isn't a parallel RLC circuit? You can't see that, we're in a bit of trouble, right? So if we were looking at the natural response of this guy, meaning that we were looking at it during the transient condition and we had turned off that voltage source Vs, what we would have is resistor R1 in parallel with capacitor C in parallel with the series combination of the inductor and resistor R3. So there's no way for us to combine resistor R1 and R3 into a single equivalent resistance and make this guy look as if it were a parallel RLC circuit. So this guy fundamentally isn't parallel and it also isn't series. So in order to determine our response, and let's just say for the sake of argument that we are looking for our capacitor voltage, let's call this guy plus VC of t here. I'm going to define some other quantities. So this is IC of t. Here's my inductor current, IL of t. And here is my inductor voltage, VL of t. And I have to pay attention to both current and voltage for the inductor and the capacitor now, because they do not have a shared quantity, right? So in series RLC circuits, everything had the same current flowing through it. In parallel RLC circuits, everything had the same voltage drop over it. That is no longer the case. So we need to keep track of 4 pieces of information now at an absolute minimum. So my goal over the next several minutes will be to develop a second order differential equation involving either the capacitor current, the capacitor voltage, or the inductor current. It doesn't matter which one I wind up getting a differential equation for, because they will both have the exact same natural response, meaning I should get the same differential equation whichever path I choose, all right? So let's talk about how we might go about figuring out what's going on here, okay? There are always going to be multiple different ways to analyze these circuits. Some are going to be easier than others, and unfortunately, it's going to be kind of a trial and error type method. So one thing that I want to be very, very clear about is that we're always analyzing these when we're determining our differential equation during the transient condition. So that means after the switch is closed, so if I have R2 show up anywhere in my equations, I've made a mistake. I want to be very, very clear about that. During the transient condition, that switch closes, which shorts out resistor R2, so R2 should show up absolutely nowhere. All right. So I am going to define another current here, and I'm going to do it in red because it's not one that I usually pay attention to. And I'm going to call this guy IR1 of T, okay? I'm doing this so that I can write a Kirchhoff's current law equation. Let me see what's in chat here. Okay, just somebody said that. All right. Sorry. So I can say that IR1, no, don't do that. IR1 of T is equal to IL of T plus IC of T, right? Just using good old Kirchhoff's current law. I can also use Ohm's law, and I could say that IR1 of T is equal to Vs minus Vc divided by R1. Effectively, what I'm going to be doing here is just developing a lot of different equations and seeing what I can substitute into other things to make things happen. It's not a whole hell of a lot of rhyme or reason to this other than using KCL, KVL, and Ohm's law in order to just not necessarily stumble into a second order differential equation, but in a sense, that's kind of what we're going to do, all right? One other thing that I'm going to do is I know that I can express that capacitor current, IC, in terms of my capacitor voltage, VC of T, right? So I could rewrite this guy as IL of T, a variable I'm interested in because I'm going to try to get a second order differential equation with respect to either my inductor current or my capacitor voltage. So I could put this as C dVc by dt like so. And I can set these two expressions for IR equal to each other, right? So that tells me that Vs minus Vc of T over R1 is equal to IL of T plus C dVc by dt. And one other thing that I can do, just real quick, this is typically what I do, is I try to get my constants on one side of the equal sign and my other terms on the other side of the equal sign. And so in doing that, I can have the following expression, IL of T plus Vc divided by R1 plus C dVc by dt is equal to Vs divided by R1. And I'm going to call this guy equation 1. It gets a special designation because it is expressed purely in terms of the capacitor current, the capacitor voltage and the inductor current, right? So I don't have any spurious variables that I don't want in. Okay. So with that taken care of, that's one equation. Another thing I could do here I can do Kirchhoff's current law, or excuse me, Kirchhoff's voltage law, and I can say that my capacitor voltage VC of t is equal to the voltage drop VL of t plus the voltage drop over that resistor R3, right? Just Kirchhoff's voltage law. So let's take care of that. So we have VC of t is equal to VL of t plus R3 times IL of t. Well, I can express VL of t in terms of my inductor current. So that would be L di by dt plus R3 I of t. So I have another equation where I have everything expressed in terms of only my capacitor voltage and my inductor current. Okay? So right now, I can actually substitute equation 2 into equation 1, right? So if I substitute equation 2 into equation 1, what I'm going to have is IL of t plus 1 over R1 multiplied by my expression for VC of t, which is L times the derivative of IL of t by dt plus R3 IL of t plus C times the derivative of that same VC of t. So I'll have L DIL by dt plus R3 times IL there is equal to VS over R1. And now I am going to distribute that factor of 1 over R, distribute this factor of C, and take this derivative, right? So I'm going to have IL of t plus L over R1, the derivative of IL of t with respect to t, plus R3 over R1 times IL of t, plus LC, the second derivative of IL with respect to t, plus R3C times the first derivative equal VS over R1. So everybody okay with the amount of algebra and all that kind of stuff that's going on? I guess technically calculus too. Did anybody see any glaring mistakes or anything? Give you guys a moment. Excuse me. So the next thing that I would do is I would group terms together, right? So for example, I only have one factor that's being multiplied by the second derivative of my inductor current. So I would have LC times the second derivative by L, which takes care of this guy. For my first derivative term, I have a factor of L divided by R1, and I have a factor of R3 times C. So that takes care of this guy and this guy. And then for IL of t, I have a factor of 1 plus R3 over R1. And this is all equal to Vs divided by R1. So anybody got any ideas of what I'm supposed to do next? Divide by LC, exactly right. So we're trying to get this thing as a second order differential equation where our second derivative term has a coefficient of 1. So if I divide both sides by LC, I get one over R1C plus R3 over L and then here I'm going to get 1 over LC plus R3 over R1 LC L of t is equal to Vs divided by R1 LC. So this guy right here is A, and this guy right here is B. So we can use our numerical values from earlier, right? So we know that A is supposed to be 1 divided by R1, so that's 4 ohms, times C, which is 0.2 farads, plus R3, which was 12 ohms, divided by L, which was 2 henries. So we get A to be 7.25, which means alpha is half of this. .625 neppers per second. Using our values, B is R3, so that is 12 ohms divided by R1 times L, which is 2, times C, which is 0.2, plus 1 over LC. So that's 1 over 2 times 0.2. So B is 10, which means omega naught is the square root of 10, or 3.162 radians per second. So what could we say about this circuit based on these parameters? It's overdamped, right? Alpha greater than omega naught means this guy is overdamped. And from here, we simply solve this circuit like we've done every other one of them, right? The only fundamental difference between solving a generic RLC circuit, and one of the ones that we've done before, is that we have to expend the effort in getting our second order differential equation instead of having it effectively given to us. So that's where the overwhelming majority of your time will be spent. All right, so because there's been a little bit of confusion about solving some of these guys, sure, absolutely. We're going to go through and we're going to work this guy and solve for a specific quantity. So let me, if I can, look at our original circuit and let's define a quantity that we might want to solve for. Actually, I tell you what, let's solve for this IR1 of t, because it's something that we've already defined, okay? So in order to solve for IR1 of t, based on what our previous analysis says, we're going to need to know what the inductor current is and what the capacitor current is. So we're going to have to put in some work here, right? So let's start by determining the inductor current. Or actually, let's start by analyzing the circuit at t is equal to 0 minus, then 0 plus, then infinity, and then work towards getting it. So at t is equal to 0 minus, our circuit looks like this. We have a 24-volt source. Here's our 4 ohm resistor. Here's our 8 ohm resistor. Our inductor is a short circuit. Here is our capacitor, C at 0 minus. Here is where our capacitor current, IC, is. So who can tell me what any of these quantities are going to be? IC has to be 0. All right. VL also has to be 0. Okay. What about our other two quantities? Okay, so I believe that you're correct, but tell me why. Oh, wait. Oh, yeah, okay. All right, so we're saying that IL is equal to 1 amp because the 24-volt source sees 4 ohms in series with 8 ohms in series with 12 ohms. So 4 plus 8 is 12, plus 12 is 24. So 24 volts divided by 24 ohms is 1 amp. Okay, that seems reasonable. That should be able to tell us what VC is pretty easily then as well, right? 12 volts. Because it's going to be the same as the voltage drop over the 12 ohm resistor, or we could simply use voltage division and say that half of the voltage drops over that 12 volt. So there's going to be that 12 ohm resistor. All right. So our analysis at t is equal to 0 minus is complete. Everybody okay with this? Nothing too wild or crazy, right? at t is equal to 0 plus. Our circuit is going to be similar, but our 8 ohm resistor is shorted out. So recall that when our switch closes, that resistor gets shorted. So we have our 4 ohm here. We have that short circuit there. We have our 24 volt source here. Our inductor is going to look like a 1 amp source direction down. VL at 0 plus is an unknown quantity. Then we have a 12 ohm resistor here. And our capacitor is going to look like a 12 volt source. And this is my capacitor current IC at 0 plus. So, just to be clear, we need VC at 0 plus, which we know has to be 12 volts. We need to determine IC at 0 plus. We need to determine VL at 0 plus, and we know that IL at 0 plus has to be equal to 1 amp. And we know those two quantities because those quantities cannot change abruptly. So, which of those quantities do you guys want to do first? I see, okay? So tell me what's what. How might we figure something out here? That's far too much work. All right, so what is the voltage drop over the 4 ohm resistor? 12 volts, right? Because there's 24 volts on one side and 12 volts on the other side. So 24 minus 12 means there's a total voltage drop of 12 ohms. 12 ohms divided, or excuse me, 12 volts divided by 4 ohms means there is a current of 3 amps flowing through that resistor, correct? So I can say that this current is 3 amps. So I have 3 amps entering that topmost node. 1 amp branches off and flows down through the 12 ohm resistor. So what is IC? 2. Mesh was too much work. Far, far too much work. Okay. How do we get VL at 0 plus? That is incorrect. Do Kirchhoff's voltage law around the right-hand loop. Tell me what turns out. So we would have 12 volts is equal to VL plus 12 times 1 amp. So 12 is equal to VL plus 12. What's VL? 0. We could have also done Kirchhoff's voltage law around the left-hand loop, where we would have said there's 24 volts being supplied by the source, there's a 12 volt drop over the 4 ohm resistor, there's another 12 volt drop over the 12 ohm resistor, so there's no voltage drop over VL. All right, so our circuit analysis for t is equal to 0 appears to be finished. Everybody okay with the answers that we have got? All right. So now let's look at what's going on at t is equal to infinity. So at t is equal to infinity, our inductor is a short circuit again, and our capacitor is an open circuit again. Our switch is still closed, so our 8 ohm resistor is still shorted out. And so that leaves us with the following circuit. Here's the short circuit representing our inductor. Here's IL at infinity, VL at infinity. Here's our 12 ohm resistor. Here is our capacitor. It's an open circuit. Here's VC at infinity. Here is IC at infinity. And let's see, VC at infinity, IC at infinity, VL at infinity, and IL. All right, so low-hanging fruit, getting taken care of. IC has to be 0 because the current flowing through an open circuit is always 0. Similarly, VL has to be 0 because the voltage drop over a short circuit has to be 0. So who can tell me what the other quantities are going to be? IL is 4.5, okay, or 1.5, yeah. So 24 divided by 16 is 1.5, so that checks out. So VC at infinity has to be what? 18, 1.5 times 12. All right. So we know that we have an overdamped circuit. We know how it behaves at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. So now we can start taking care of things. Before we move along to the first step or the next step, though, we need to go ahead and calculate S1 and S2 because they're going to play a role in setting up our system of equations since we have an overdamped circuit, right? So S1 is negative alpha plus the square root of alpha squared minus omega naught squared. So let's see here. So that's negative 5.397 units per second. S2 is negative alpha minus alpha squared minus omega naught squared. Wait, did I screw that up? I did, I apologize. That value should be S2. I put the wrong sign in. So this should be negative 5.397. And S1 is supposed to be negative 1.853. It is critically important that S1 is the one with the plus sign and S2 is the one with the minus sign. You should expect that they're both going to be negative. By definition, they have to be, or we don't have exponential decay, we have exponential growth, which is not at all what we should expect. And you should see that the magnitude of S1 should always be smaller than the magnitude of S2. Just want to be very clear on that. All right, so now that we know what S1 and S2 are, we're in good shape. So because we're looking for the resistor current that is going to be given by the sum of the inductor current and the capacitor current, which quantity do you want to deal with first? The inductor current or the capacitor current? Inductor current. Okay. So, put a line there. For our inductor current, we know that IL of t if I can write without pressing this button or somehow opening up my mail app again, is of the form A1e to the S1t plus A2e to the S2t plus IL at infinity, because we have the source still left in, so we have to make sure to include this infinity bit here. At t is equal to 0, this reduces to A1 plus A2 plus IL at infinity, which gives us an equation that says that A1 plus A2 is equal to negative 1.5 amps, right? So A1 plus A2 plus 1.5 is equal to, oh, no. I've done something dumb here. Done something very dumb. All right, IL at 0 plus was not 0, it was 1. So we have 1 amp is equal to A1 plus A2 plus 1.5 amps, which gives us A1 plus A2 is equal to negative 0.5 amps. There we go. Apologize for my short circuit. We know that our inductor voltage, VL of t, is L DIL by dt. So that means it will be of the form L times S1 A1 e to the S1t plus S2 A2 e to the S2t at t is equal to 0. This reduces to L S1 A1 plus S2 A2. And so this is giving us VL at 0 plus was 0 volts. So so S1 A1 plus S2 A2 is equal to 0. That's our second equation. I got rid of the L by dividing both sides by L, where 0 divided by L is still 0. So it's just me being lazy. All right, so I now have two equations, two unknowns, so I'm going to use my system solver here. So I have 1A1 plus 1A2 is equal to negative 0.5. And then I have S1, which I have stored as variable A, plus S2A2 is equal to 0. And I solve, and I get A1 is equal to negative 0.76, 1 amps, and A2 is equal to positive 0.261 amps, which tells me that IL of t is equal to negative 0.61 e to the minus 1.853 t plus 0.261 e to the minus 5.397 t plus 1.5 amps. And so at t is equal to 0, this looks like negative 0.761 plus 0.261. So that's going to be negative 0.5 plus 1.5 is equal to 1. So that all seems to check out. So there is our inductor current for our capacitor voltage. Question, comment? Okay. All right. So capacitor voltage is going to be a similar process. VC of t is going to be A1e to the S1t plus A2e to the S2t plus VC at infinity, which means VC at 0 is A1 plus A2 plus VC at infinity. So VC at 0 was 12 volts, is equal to A1 plus A2 plus 18 volts, giving us A1 plus A2 is equal to negative 6 volts. For equation 1. Then we have IC of t is equal to C dV by dt. So that's going to be, C times S1 A1e to the S1t plus S2 A2e to the S2t. And so at t is equal to 0, this becomes C times S1 A1 plus S2 A2. So that's going to give us IC at 0 plus was 2 amps. Is equal to 0.2 farads times S1A1 plus S2A2. So we now have 2 equations, 2 unknowns. So let's go ahead and throw this into the solver. All right, so let's see. I have 1A1 plus 1A2 is equal to negative 6. I have S1 times A1 plus S2 times A2 is equal to 2 divided by 0.2. So I'm just moving that C to the other side so that I can put stuff in my calculator more easily. Thought I could. There we go. Solve this guy. And I get A1 is equal to negative 6.315 e to the minus 1.853 t plus, oh sorry, I mixed my steps up there. A1 is negative 6.315. A2 is positive 0.315. These are both measured in volts. All right, and so from here, IC of t, my first coefficient is going to be C, which is 0.2. Times S1 times A1. So I get 340 e to the minus 1.853. My coefficient for my second term on my current is going to be 0.2 times S2 times A2, which is negative 0.340 e to the minus 5.398 t amps. Right? I should not have a DC term here because my inductor current does not, excuse me, my capacitor current does not include a DC term because it's based on the derivative. So finally, I R1 of t is IL of t plus IC of t. So I simply add these guys together. So that's 2.34 plus negative 0.761 is 1.579 e to the minus 1.853 t. And then I have negative 0.340 plus 0.261 is negative 0.079 e to the minus 5.398 t. And then I also have to add my DC term. So plus 1.5 amps. And that is my answer. So I guess one simple and quick way that we could figure out whether or not so at t is equal to 0, it looks like this resistor current should be equal to 0 as well, right? So t is equal to 0 plus. No, you're right. Yeah, it should be equal to 3. 1.5 minus 0.79 plus 1.5. So it should be equal to 3. You're absolutely correct. And that is exactly what we got. So everything on that end checks out. Yes.
We also define IR as VS minus VC over R1. Can we do it like that as well? You have the VC.
So VS minus VC over R1. Okay. So our source voltage would be 24 volts. So let's see here. All right. So we could split that up. That is a fantastic point, actually. So 24 divided by R1, which is 4, gives me 6 volts. Hold on. So VS, 24 volts, divided by R1, is 4 ohms, means I should have a DC current of 6 amps, and then I'm going to have subtracting this other thing. So that would be, let's see what's happening here. Let me do it in a different color. Oops. Why is it trying to erase? Sorry, it's giving me a ludicrous amount of lag right now for some reason. So 24 volts divided by R1, which is 4 ohms, minus VC of t. So we don't have VC of t just yet, but we could figure it out because we know what A1 and A2 are, right? So A1, sorry, let's scroll down here, is negative 6.315 volts. All the way back up here. Negative 6.315 e to the minus 1. Can't seem to remember that number, 1.853 t. plus A2 0.315 e to the minus 5 point something. So 5.397 t. This is all divided by that same. Wait, actually, I take that back. R1 is 4 ohms. But we also have to take into account that our capacitor voltage does have some value at infinity, right? Which was 18. Okay. So let's come down here. So I'm going to have positive 6.315. So 6.315 over 4 is 1.579 e to the minus 1.853 t. Then I have negative 0.315 over 4, which is minus 0.079, if my pen will write. E to the minus, I'm just going to write S2T here, because we know what S2T is at this point. Then we have 24 divided by 4, which is 6, minus 18 over 4, which is 4.5. 6 minus 4.5 is plus 1.5 amps, which is exactly the same thing. Yep. So if I would have recognized that equation that we had written earlier, we could have actually shaved off a considerable amount of calculation time here by just using that expression. Yeah. So we only would have needed to calculate VC of t, and from that we would have been able to get the exact same answer that we got using our Kirchhoff's current law expression. So always going to be multiple different ways to get these kind of resistor currents and all that kind of good stuff. Another potential route would have been using a KVL expression if we wanted to, and then back calculate. But it's all good. We got the right answer both times. That's another great way to make sure we didn't screw anything up. So I think that is enough out of me for today. When we get here on, today's Wednesday, right? So Friday, we're going to cover another case. So it's going to be another similar lecture, except that we're going to look at a circuit that has 2 capacitors or inductors that cannot be combined. So it's still 2 energy storage elements, but it's not going to be an RLC circuit per se. It's just going to be a generic second order circuit. All right, you guys have a great rest of your day. Again, only homework 7 is due today at 5. Homework 8 is due on Friday.